Today I want to talk a little bit about colligative properties and solve some problems that are representative of the types of things that we can measure in the lab and the way that these various characteristics are all interconnected with each other. So colligative properties are properties about a solvent, usually a liquid, that change with changing concentration. So when you mess with the concentration of a solution compared to the pure substance, whatever it is, then if you add solute, the freezing point goes down, it depresses, and the boiling point goes up, or it elevates. So we talk about freezing point depression, boiling point elevation, and they're related to the molal concentration. So molality, which is the number of moles of solute per kilogram of solvent. So you might see a problem that looks like this. The freezing point of pure acetic acid is 16.60 degrees Celsius, and it asks what the freezing point of a solution is. So if I have some sort of solute in there with a concentration of 0.250 molal, and acetic acid is my solvent, then how does it change? What is the new freezing point? Well, we know in concept that the freezing point is going to go down, so we're expecting that this is going to be lower than the pure. But how do we do that? What is the relationship? Well, the change in the freezing point is usually symbolically represented by a delta, right, as a change of the freezing temperature, and that's related by some constant. So this is just called the freezing point depression constant. And that constant is specific to the solvent. So if I had an aqueous solution, then water would be my solvent. That has a specific K value. For acetic acid, I'd have to go and look it up, and what I'd find is that the freezing point depression constant for acetic acid is 3.59. Now the units on this are in degrees Celsius per molality, so it looks like this. And again, that underlined M there indicates that it's the number of moles of solute per kilogram of solvent. And then that is multiplied by this C sub M, which is concentration, molal concentration. So if I wanted to find out by how much the temperature goes down, then this is what I can use. And if I'm looking at the difference between the two, then I can think about it as, what is the difference between the pure substance and the solution? Because that difference will tell me by how much it goes down. So I could say, well, here's my pure, my freezing point of my pure minus my freezing point of my solution here. And that's equal to some constant K times my molal concentration. So I can kind of unpack my delta T there. I could also just solve this thing for the delta T and then compare it to the original. So it would just tell me by how much this is going to go down. That would be fine too. But if I rearrange here and plug and chug, then I can say, well, the pure solution is this, 16.60 degrees Celsius minus the solution, which is what I'm solving for. My K value is something that I looked up from a table somewhere. And I'm going to multiply that by my concentration that's given from this whatever solute I dissolved in there. And now if I just do some algebraic rearrangement, subtract this guy from both sides, divide by -1, then I end up with my freezing point of my solution, is 15.70 degrees Celsius. So this is just, again, with the way that I've solved it, I decided to leave the number in there. I could have left this on its own, and it would give me the difference between the two. So that would be, 0.9 difference, and that would have been my delta T, and then I could have said, well, if I subtract that amount, then I'll get to this, get to my pure acetic acid's freezing point. So that's the relationship there. This is kind of this is our big message. This is why molality is so important, because these constants in dealing with the colligative properties can be kind of plugged into these pretty straightforward algebraic relationships and solving problems that look like this. All right, let's look at another one. So we have a solution that is made by dissolving a solute. So we have some sort of unknown solute that we're dissolving into water. So we're making an aqueous solution. And in the lab, using freezing point depression, because that's one of the ways we can do it, we know the freezing point of water at 0. In the lab, I figured out the freezing point depression by how much it went down. I know the constant, so that gives me my concentration. So that's a good way to solve for a concentration also in the lab. So I found that, and it wants to know the molar mass of my unknown. So this is another way that we can use freezing point depression. The technique can be used to find these concentrations when we don't necessarily know what they are, especially because we don't know what it is, right? I dissolved some unknown powder in there, so I can't just convert to moles like I normally would if I actually knew what it was. I had to determine it experimentally. Okay, so it's asking for molar mass. So I need to figure out what I'm missing. Molar mass, of course, is the number of grams in 1 mole of that thing. I have the number of grams, so that's kind of part 1. So what I really need to solve for is the number of moles of my unknown. And that'll come from my molality here, because I know that I have 25.4 grams of my water. So if I start there, 25.4 grams. And if I convert from grams of water to kilograms of water, and then I use the molality to go from kilogram of water to moles of my solute, then that'll get me at what I'm looking for, right? I know my number of grams. I need to find my number of moles of solute, so I can do that using dimensional analysis here. So that gives me whatever my substance is. I have 1.42 times 10 to the negative 3rd moles of it. And then if I take my mass, because that's going to give me my molar mass here, so 0.131 grams divided by my 1.42 times 10 to the negative 3rd moles, then that gives me 92.3 grams per mole. And there's my molar mass. And if I had kind of a table of options, if I kind of had a sense of what it was, then this would be one way to figure out what my unknown substance was in this particular context. So again, kind of a cool application of freezing point depression. Now the other colligative property that I want to talk about is boiling point elevation. So boiling point elevation is when you add a solute to your solution. The pure substance has a specific boiling point where the atmospheric pressure is equal to the vapor pressure of your substance, and it starts to boil. And it has the same relationship that we saw for freezing point depression. So we look at the change in temperature for boiling, so a little sub B there, and that's going to be equal to some constant K, usually a K sub B, again for boiling point, times the concentration in molality, so the molal concentration. So this K value is called the boiling point elevation constant, aptly named. Elevation constant. And then the kind of C sub M here is concentration in molality, so the molal concentration, which is the number of moles of solute per kilogram of solvent, and that's equal to this change in the boiling point. So by how much is the boiling point going up from its normal amount? So if we look at this problem, I have 0.205 grams of white phosphorus, and it's dissolved in this solvent. So this is carbon disulfide, and I have 25 grams of it. The boiling point is found to be this much higher than the pure substance. So this is my delta T sub B here. This is by how much my boiling point is changing. And so it wants to know the molecular mass or the molar mass of the phosphorus in the solution. So I have grams again, so I need to know my number of moles. So the first thing that I need to do is to find my concentration, because that's kind of the missing piece here. I know how many grams of my solvent I have, so if I can figure out my concentration, then that will get me at the number of moles of my solute that I have, and then that'll give me grams per mole, which gives me my molecular mass, which then from there I can figure out the chemical formula of. So one step at a time. We have our boiling point elevation. So this is the change in my boiling point. It went up by this amount, and that is going to be equal to a constant. So I need to look up my boiling point constant for carbon disulfide. So when I go to the tables, then I find that my boiling point elevation constant for CS2 is 2.40, and that's degrees Celsius per molality. And then that is multiplied by my concentration. So that's kind of what I'm solving for. I'm trying to figure out the molality. So if I just do my little rearrangement here, then I find that I have a concentration that is equal to 0.0663 molal. Now I can kind of do the same operation I did in the last problem. I know that I have 25 grams of my solvent, my CS2, and then I can go from grams to kilograms of my CS2, and then using my molality, this is the number of moles of phosphorus per kilogram of CS2, carbon disulfide. So 1 kilogram of CS2 on the bottom, this many moles on the top, mole. And this gives me this 1.66 times 10 to the negative 3 moles. And now I can take the mass that I was given to start off with, 0.205, divided by my number of moles. That'll give me grams per mole. Per mole. And that solves question 1, which is about molecular mass. And that gives me a molecular mass of 123.49 grams per mole. I kind of grew some sig figs there, right? I'd have 3 sig figs in this thing. So if I actually rounded this thing to 3 significant figures, it would round down to 123 grams per mole. And then if it's asking me for my chemical formula, then I need to look at how phosphorus itself compares to this. So when I go to my periodic table and look for just one phosphorus atom, then I kind of go here and I see it's 30.97 is one of them. So that's my AMU here. So if I look at this guy and compare it to what I have here, then I obviously have more of them, right? So if I figure out by how many, I divide this by this, then I end up with 4, which is a nice round number. So how many times does that 1 go into this number? That gives me 4, so that means that my chemical formula for this white phosphorus is P4, which has kind of a wacky shape to it. It has a bunch of trigonal pyramid coordinated phosphorus atoms that are all connected together covalently, which is kind of interesting, kind of a weird shape. Okay, so that's another application for this kind of calculation. So these boiling point and freezing point expressions, again, are pretty straightforward, right? We're just looking at the change in the temperature. It's related by a constant and that molal concentration. So if you can get to that molality, then you can figure out how much you're going to be tweaking that boiling point or freezing point. Now, if you have any questions on this, don't hesitate to reach out. Otherwise, I'll talk to you again soon.